The total volume under a density surface is supposed to be 1. Now let's see how we would go about checking that. So supposing I have a density surface, at least I'm claiming it's a density surface, which is defined by the formula given. I've drawn a nice picture of it, and the picture, while it's lovely, does not help us find volumes. So for that, we have to use calculus. And we have to draw our own picture, for which we are invariably going to draw just the set of possible values. Now the possible values are everything's happening between 0 and 1, and y is less than x, which means that I'm looking at a triangle. I have x here and y here. And what are the values of y? Also 0. Let's get a few dotted lines going. Y is also between 0 and 1, and all of the probability is in that solid triangle. Everywhere else, it is 0. Now, we need to integrate the joint density function, and so I'm going to start writing out how you do a double integral. It's like a double sum. You first hold one of the variables constant and sum over the other one, and then you sum over the first one. So why don't we decide that we have to first make a decision about which variable we're going to hold constant. So I am going to decide that I'm going to hold x constant, say there, and I'm going to integrate out y first. And then I'm going to integrate out x. So you can think of this as two integrals. The inner integral and then the outer one. Well, now the inner integral isn't very well defined yet. We have to figure out the limits of the integral, and we can see that with x fixed where it is, y can be any of these values. And so the smallest that y can be is 0, and the biggest that it can be is this value right here, which is x, because this is the x equals y line. And so y for the fixed x goes from 0 to x. And now you have to think about where you could have fixed this x. Well, you could have fixed it here, or here, or here, or here. You could have fixed it anywhere between 0 and 1. And so now you have a calculus problem, which is you have to calculate the following integral: 0 to 1, 0 to x, 24 x minus y times y, in the order first integrate y, then integrate x. Now the answer better be 1, and we have to crank it out. So I will invariably do these without this leading constant, and then deal with the constant at the end. So I'm going to look at the integral of everything except the factor of 24. Right, so the inner integrals are xy being integrated with respect to y from 0 to x, and then y squared being integrated with respect to y, also from 0 to x. And so in my first inner integral, the x is a constant, so I pull it out, and then I'm integrating y from 0 to x, so I will end up getting x squared over 2 as my integral. And I have to integrate that entire product dx. And then in my second inner integral, I am integrating y squared from 0 to x, and so I'll get y cubed divided by 3. I'm sorry, x cubed divided by 3. And so I now have a half, and I'm integrating x cubed from 0 to 1, so I will get a quarter. And here I have a third, and I am integrating x cubed again from 0 to 1, so I'll get a quarter again. And lo and behold, I have an eighth minus a 12th, and that's 1 in 24. That's where that 24 comes from. And it reminds you the point of the multiplicative constant outside density. It's there precisely to make the thing integrate to 1. What we've shown is that without the constant, the function integrates to 1 in 24. So you have to multiply by 24 to make it integrate to 1. You're in good shape. You could have tried to do this integral in the opposite direction, choosing to integrate x first and then y. We'll just write out that integral, and I'll let you crank out the calculus yourself. So if you had done it in the opposite order, let's draw our region first. That is your x equals y line, and y can be any number between 0 and 1. And so now what we're going to do is we are going to fix y first and integrate out x. So we're going to try and do so we're going to fix y, and we're going to integrate out x, and then we're going to integrate out y. All right, so let's look at the limits. For the inner integral, y is fixed, and you're looking at how x could vary. Well, if y is fixed here, then the biggest x can be is clearly 1. It's right here. And the smallest x can be is this value right here, which, if that's y, then this value here must be exactly the same. And so x goes from y to 1. And now I have to think of where I could have fixed this y. Well, I could have fixed it anywhere here. And so I could fix it anywhere from 0 to 1. And so this is an equivalent calculation of the total area, and you will end up having to do which you can do similarly to how we did it the first way. I think this way is longer, but you should have a go. The main thing for you to note is that you have to integrate the joint density, and the only thing left is geometry. Figure out where the joint density is defined, and then very deliberately fix one of them and fix one of the variables and see what is the smallest the other one could be and what is the biggest. There's really nothing else to it. It's a geometry problem. And then there is the calculus of actually doing the integral. So that is what we did right here. We did the geometry here, and then we took a little time to do the calculus. But where's the probability? The probability is only here, in that you have to integrate the joint density over the appropriate region. After that, you fall back on your math prereqs.